Uh, Welcome back. We will start our second lecture for today, given by Anil Hirani, continuing on discrete exterior calculus.
So lecture 2, and last time we did everything which does not, many things that don't require metric, and today we'll introduce metric and see how it enters into exterior calculus and then how it enters into discrete exterior calculus. And like before, for the smooth part, we will use intuition and informal, and then for the discrete part, I'll be very precise. So, but before I start, let me remind you that, so we had this, what we introduced was that the manifold was discretized as a simplicial complex. The K forms on the manifold were discretized as K cochains, and the exterior derivative was discretized as the co-boundary operator, which we still write this way. So the co-boundary operator was defined by duality to the boundary operator, which has very simple geometric meaning. And as we saw for things like, if I have an edge is my vector, is my simplicial complex, and I have a function which takes values at the vertices, a zero form, then its D will be just the difference, and it will take its value on the edge. And then I introduced the discrete wedge product and showed how there is Leibniz rule, and then there is naturality. This pullback naturality with respect to simplicial maps. This idea of D commuting with pullback and the wedge commuting with pullback is called naturality for some reason. So now we want to do, of course, reduce everything to linear algebra eventually, even so we'll have matrices. So for example, the D will be represented as a matrix in the programs. So for example, so D, let's say, goes from A cochains to K plus 1 cochains. So take a basis for, so this is a just ordinary real vector space. And let's say you have nk number of k simplices and nk plus 1 number of k plus 1 simplices. Then it's just a real vector space of dimension nk. You can take as basis a cochain that takes value 1 on a particular simplex, k simplex, and 0 everywhere else. Like, let's say you are working on a tetrahedral mesh and you want to look at C2, so things that live on the triangles. So take a cochain which takes 1 on one triangle, 0 on all the other triangles. And so that forms a basis. So in that basis, you'll have a basis here and a basis here. Then you can write down this D operator in those bases. And it will turn out to be a matrix with zeros, ones, and minus ones, because it comes from the boundary operator. In fact, it will turn out that it will be just the transpose of the boundary operator, the appropriate boundary operator. So you will see this in the tutorial, which is, I believe, at 4:30 today. 4:30 today. So Kaushik and I will introduce PyDeck, which is a Python library which one can use to do discrete exterior calculus and the lowest order finite element exterior calculus. And we've been using this in our research for many, many years. Okay, so now let's start talking about metric and how that enters. So now we will have on a manifold a metric. So we have a Riemannian manifold now, so that we have a way to measure lengths and angles on the tangent spaces of the manifold. And so the way this metric will enter into exterior calculus is via various operators, but the main one of which is called the Hodge star operator. And then the other two that are important in this setting are called musical homomorphisms, because they look like the flat and the sharp. So Hodge star, flat and sharp, this will lead us to talking about codifferential, defining the L2 inner product on a manifold, which allows us to do integration by parts, which allows us to do weak forms. So you can see how the whole Laplacian stuff flows out in DEC and FEEC in exactly the same way. The only differences are that we have mass matrices which are diagonal, and you will see that PEEK has mass matrices which are sparse but not diagonal. So that forces them to do mixed form, whereas we can do both direct and mixed for all Laplacians. I mean, I'm not advocating one or the other, I'm just pointing out the differences. Okay, so let's start with...
Anil, sorry, a quick clarification on what you just said. So
yeah.
Just to make sure I'm following. Did I understand you correctly when you said that all the way you will formulate it, the mass matrix will always be diagonal?
Yes, the way I'll formulate it, the mass matrix will always be diagonal.
Independent of what the actual system of equations you're solving?
Yes, yeah, because we are discretizing the Hodge star.
Okay.
That's a unique thing. So for the given metric, there's a unique isomorphism, and that's what we are trying to discretize, independent of what differential equation. So this is the whole philosophy of DEC and FEEC, although they're motivated by solving Poisson's equation, but the idea is, let's look at every operator, every object, discretize, preserve properties, see what happens.
Okay, and because it's the Hodge star, so that has the volume form in it.
The metric gives you a volume form that I will mention.
Okay.
And that is a unique volume form once you pick the orientation.
Yes. Okay.
Yeah. Okay. So let's see, where should we start? So I guess maybe this is the right place to start. So remember that we use this to represent smooth vector fields on M. So this operator sharp is a map that takes one forms to vector fields. And this uses the metric. This is a metric duality. And the way it uses the metric is that, so I'll just write metric using this inner product notation. If you wish, I will write a little G there. So given a one form alpha, so suppose I have a one form alpha, I want to produce alpha sharp, which will be a vector field. So that it's the one, it's like the Rees representation theorem type of thing. It's the one such that if you dot it with, if you take the inner product with any other vector, you will get the same answer as alpha would have produced. So the reason people call it sharp often is that when you write covectors, you write horizontally, vectors vertically. So you take a flat object and sharpen it like a sword. And then there is the flat operator, which we will eventually need. So this goes the other way, and it's an inverse of that. It takes a vector field and produces a one form. So if I have a vector field here, I will get a one form here. And this will be, again, the one form such that its value on any vector will be the same as what taking the inner product for all y. So the reason I had to introduce this is so that I can talk about inner product of K forms. There's an inner product that's induced on the space of K forms. And you obviously need that if you want to do anything in PDEs. You want to take inner products and integration by parts and things like that. Okay, so the way you want to define the inner product, so suppose you have alpha and beta are K forms, and we'd like to induce from the metric some inner product on K forms. I'll keep writing just angular brackets for this. So these forms are antisymmetric tensor fields on the manifold. When you take the inner product, you'll get a number at every point, so you'll get a smooth function. So the result is a zero form. And the way it's done is by noticing that, which I won't prove, but every K form can be written as a linear combination of wedge of K1 forms, for example, by using a basis. So let's just write this definition for when alpha, let's say, is alpha 1 wedge ... alpha K, and beta is beta 1 beta K. So first you define okay, so this thing is defined to be equal to the determinant of, you take alpha I, sharpen it, take beta j, sharpen it. So this is the ordinary inner product of vector field, because this is a vector field now. And do this for all the alpha i's and all the beta j's. And since it's k and k, you will get a square matrix whose determinant, do it for all ij, its determinant will be that's one definition of k forms. There is more involved ways to define them, but this is the one that I like. Yes? No, because you can pick different bases, but the inner product is unique. So, okay, so once we have that, then the next thing is that there is a volume form. So let's say you have a manifold which is orientable. You're doing a PDE, so you want an orientable, let's say orientable manifold. You pick an orientation, and there is something called a G volume. So this is a unique N form. So let's write this as mu G. So this is a unique, nowhere vanishing once you fix G, there's a unique one. Once you fix G and the orientation, there's a unique, nowhere vanishing N form. N is the dimension of the manifold, such that for any orthonormal set of N vectors, this mu of G, which are oriented in the same way as you have picked for the manifold. Like if you picked a certain orientation, then this set of vectors should match that orientation. So orientation on the tangent space can be thought of as an ordering of basis vectors, for example, and it's related to the orientation on the manifold. But anyway, so then this, you'd feed these N vectors and you'll get a plus one. So using this G volume, which is a unique volume form, once you fix the metric, we can now define the Hodge star. So Hodge star is the unique, so this is called, Hodge star. So it's an isomorphism between K forms and N minus K forms. And it's unique. There's of course one for every K. So maybe sometimes you can write an index. And this is N choose N minus K, which is equal to that. So when we discretize it, we will end up with square matrices. So this Hodge star isomorphism is defined as the unique map between these two, which satisfies this alpha wedge star beta is equal to the alpha dot beta that we just defined times the G volume that we just defined. So notice that, so where alpha for all alpha beta, which are K forms. So this is K, this is N minus K, so the whole thing is an N form. Multiplication adds the degrees. By the way, these things are called degrees of the form. K is the degree K form. And this is a zero form, a function, because you take the dot product at every point on the manifold, you get a number. So in the end, you get a function, which is a zero form, and that's an N form. And so this is 0 plus N, and so at least that matches. So, so when you look at this, it's hard to see what kind of thing it is, but like in a proper course, this not being a proper course, in a proper course on smooth manifolds and exterior calculus, you would do things in Rn, R3, you would do lots of calculations with in coordinates and get some intuition for it. But luckily, as always, the discrete stuff is very intuitive. Yes?
Excuse me, I have a question on the G volume. So I don't see where the definition depends on G.
Because this is orthonormal. So this is saying that there's a unique
Normal, so
orthonormal with respect to this G. Okay. Okay, so once you have this, this allows you, when you have n forms, you can integrate them on n-dimensional things. It allows you to do an integration on the manifold. So we can then define. So this definition is a point-wise definition. Yes.
Can you give maybe a intuition for where we'll be using Hotstar? Will we?
Where?
Yeah, where in the sense, is it used to
define Laplacian? Yeah, so that's a kind of important operator. So, right. So it's used, Hotstar is used to define the codifferential, which one shows is the adjoint of the exterior derivative with respect to the L2 inner product. And then once you have D and its adjoint, you are able to define the Laplacians, various Laplacians.
But the fact that the inner product is a zero form and then you have this mu G, which is
yeah,
n form. So how does
because I'm preparing for this to be an integrand.
Okay.
Yeah, so that I can define an L2 inner product. So what I was saying is that this produces a number at every point, but to get an L2 inner product on the manifold, we want to get a single number for two different forms. And so that will be defined as alpha, beta is L2, let's say, on M with respect to this metric. So this is defined as the integral on M of alpha wedge star beta, which is alpha dot beta. So this allows us to then, it will allow us to do all of the things that we want to do for PDEs. So, okay, once we have the Hotstar, so the main property is, so if obviously if you do 2 times, you get plus minus 1, there's a sign involved, but if you do star star, you'll get identity, but turns out there's a sign. The star of 1 is the volume form, the star of the volume form is 1, things like that, which won't be important for us. What's important for us is this k n minus k isomorphism. So we would like to see that geometrically, introduce that into DEC in a very geometric, intuitive way. So let me start with a drawing. So what you do is, so now we want to do a discrete Hotstar. This discrete Hotstar will be done by introducing a dual cell complex. So what we had originally X, we will call it, so X will be the primal, we'll call it the primal mesh or primal simplicial complex. So X is always for us a simplicial complex. But it's a geometric dual, which I'm about to define, which we will write as star X. This will be, we'll call this a dual cell complex. We will see that in general, it's not simplicial. It won't just have triangles, but it turns out that it's built from a simplicial mesh. And that simplicial mesh comes by first subdividing X and then gluing certain things together. So that's the construction that I want to show here first. So let's say you have, for this part, we will assume that X is well centered. That's a phrase that we introduced many years ago, which means that the circumcenter should be in the interior of the simplex, which is a very rigid requirement for meshing, but I will relax that later. But for now, for simplicity of understanding the story, it's better to assume that the circumcenter of every simplex is inside it, in the interior. So for example, in 2D, this means acute triangles. If you recall your ninth standard geometry. So what is a circumcenter? Circumcenter is the unique point which is equidistant circumcenter of sigma, a simplex, is a unique point which is equidistant from all its vertices. So if you remember, the way you do that is for a triangle, you want to find something which is equidistant from all the vertices. So you bisect this thing. Now everything on this line will be equidistant from this. Then you bisect these. This will be equidistant from that. So their intersection will be equidistant from all three. And there are similar constructions in higher dimensions. Yes. If you wish. But everything will work if you have each triangle living in its own local space, and then you have gluing information. The gluing information will allow you to build the exterior derivative without embedding. And even without embedding, we'll be able to get this.
To have the idea of circumcenter.
Yeah, so each simplex is living in Euclidean space, yes. But it doesn't have to be in some sort of fixed Euclidean space. It can be some. And in fact, people have played with non-Euclidean. So like, for example, there's a group in Finland which has used DEC to do space-time hyperbolic PDEs using Minkowski in a product, which is not even an inner product. Yeah? So anyway, so let's take an acute angled triangulation for now. And you first do a subdivision by finding the circumcenter of every simplex in this. So including the edges, and think of the center of the vertex as the vertex itself, the center of every edge, and the center of every triangle, the circumcenter. So you can do this duality construction using other points like barycenters. And in fact, in algebraic topology, you will see the barycentric subdivision is used to prove Poincaré duality, like in Moncrief's book. I, in fact, borrowed his notation. But instead of barycenters, we use circumcenters because we want the metric information to somehow enter the picture. And when you use circumcenter, because of this construction, these lines are perpendicular, and so we'll use this information about angles and lengths and volumes, which will incorporate the metric in this indirect way. I mean, it's possible that you could do a regimetric of different kind, or like piecewise constant metric, which is different from Euclidean, and we haven't played with that, but in principle, you could make dual meshes using that too. But let's just do everything in Euclidean. So then you do a subdivision by, so with these new vertices that you have, so we had X, and we'll call this, what we are building, we'll call this the circumcentric subdivision of X. And what you do is you start at the vertex, go to every edge on which the vertex lies, then go from that edge to every triangle in which the edge lies. And you can do this in any dimension. So you start here, go here, go here. That gives you one triangle. But there are other edges. And in fact, this edge and that triangle, start here, go here, do this. Start here, go here, do this. So when you do that, you'll get this subdivision. Every triangle will get subdivided into 6. And if you were doing this for tetrahedra, you would have 24 tetrahedra, and so on. So then, once you have that, you will glue these to get this dual cell complex. And the way the gluing is done is you glue all the simplices of dimension n. So let's say if you want to find, so what we are defining is the dual cell for every K simplex. So the dual of a vertex will be all the triangles that you got by starting from that vertex. So this will be, if you glue these all together, you will get this region. So it turns out that if you are in a planar domain or in R3, this will be the Voronoi region of that vertex. If you look at the vertex sites, this will be the Voronoi region of that. So this shaded region will be the dual of this central vertex. Similarly, the dual of this vertex will be this part, if this is where the mesh ends. The dual of this vertex is this. So for a zero-dimensional object in our primal mesh, we are getting an n minus 0, i.e. two-dimensional object. And similar things will happen in all dimensions. Then if you want to do the dual of an edge, you start from its center and then go up till you reach the top dimension. So for example, the dual of this edge, if you want to find the dual of this edge, you start from its center and then go up in dimension. So this will be the dual of that, the line joining the two circumcenters. And if your mesh is a surface embedded in R3, for example, so let's say you have this mesh, then this dual will be broken, and that's okay. It doesn't have to be a straight line. The Voronoi regions will not be real Voronoi regions in R3, but they will be intrinsic Voronoi regions. So they will not be a planar polygon, but it will be the set of all points closest to that vertex. So here the dual will look like this, and that's okay. All we care about is the angles and so on, the lengths. So then the DEC Hodge star is defined as a map. So by the way, this, when you put these together, you get a cell complex, which has formal definition and whatnot via CW complexes, but we don't need to worry about that. But you can imagine that you have these cells and there's going to be a notion of a D on these things. So what we will do is our primal cochains, now we will have dual, so for K cochains, and we'll have, for example, N minus K dual complex. So when we put all this together, instead of a simplicial complex, we just call it the dual cell complex. And the Hodge star will be the following. So given sigma, a K simplex, the star K will be a map. We will think of it as a map from CK to Dn minus K star K. So since for every edge there is, so for every K simplex, there's an N minus K dual objects. So they are the same in number. So you will get, there are Nk of that, there will be Nk of these. So it will be a square matrix. And the entries of that square matrix, so for a particular sigma, the entry corresponding to this sigma will be in this matrix, this diagonal matrix that you just, in the diagonal corresponding to this sigma, you put the length or the, so I'll just use this notation to denote the measure of this object, whether it's length or area or volume. And the measure of a point will be taken to be 1. So it will be this divided by that. So you'll get a diagonal matrix Nk by Nk, and every entry on the diagonal will be the ratio of the dual of that simplex to the primal. Question?
So D and K,
Yeah.
these for dual or?
These are the dual cells. So for let's say if we are talking about the sorry, the dual cell complex is this. These are cochains. These are dual cochains. These are cochains and dual cochains. Not the cell complex is this, but these are dual cochains.
But the dual cochain is isn't it a cochain on the dual?
Yeah, these are cochains.
So we could call it C and K of star X, no?
No, we like to use D because dual. So just we remember.
Okay.
Yeah.
Same object.
Yeah, same object. Yeah.
So the fact that you have a diagonal matrix is instead of just, let's say, n scalars associated with the dual cochain.
Yeah.
Is that going to play an important role?
Yeah, its role is in efficiency. So like if you're doing an electromagnetism problem which is time dependent and you have to do the inverse of the mass matrix, it's pretty hard to do that in finite elements. And we recently proved that the inner product induced by this converges to the finite element exterior calculus mass matrix, the inner product induced by that. And that allowed us to prove everything, stability, convergence. Hodge Laplace problems. So for a long time, it was a mystery. I mean, why should one do this? But it just seems cute, and it seems to produce numerically. When you do the numerical computations for Hodge Laplace problems, you get, and you measure the order of error. So Kaushik had done many things in his thesis where numerically they look like they have the same order as the lowest order finite element. But it was only recently that these two groups have proved the actual conversion.
Are you going to get, if you discretize a domain, are you going to get a bigger mass matrix than you would in a traditional finite element method because of this, the fact that you have a diagonal?
No, it will be the same size, exactly same size. It will just be diagonal rather than sparse, but not diagonal. I will actually construct the finite element one just so that you can, because it's a tool that one can use as a shape function. Like the Whitney forms is a tool one can use not only as a shape function, but also to measure L2 error in the whole domain, because you only have information in DEC at the degrees of freedom. So, but you can actually spread it out on the whole thing and then measure L2 error, H1 error, things. Oh, this is not a norm, it's just my notation for measure. So for example, the dual for this edge will be the length of the hot star entry for this edge will be the length of this edge divided by the length of that edge. The hot star entry for this vertex will be this area of this pink thing divided by 1. Yeah, that is going to bring it. So the metric has entered in two ways. One is via angles and one is via measures like lengths and areas and so on. There is no explicit G that we construct. Yes.
So you've mentioned Laplacian a few times and where some of these operators will play a role in defining the Laplacian.
Yeah.
Will you also talk about other like vector derivative operators, divergence, gradient?
I will write down divergence, gradient, and curl in terms of exterior calculus once I do the codifferential, and then you will see why there is so much metric mixed in with these vector calculus operators. It just, we don't see it because we normally use Euclidean metric. So it looks very simple, but if you were using some non-Euclidean metric, then the expressions are horrible. I mean, relatively speaking. Yeah, I will show div grad curve.
Will there be examples, or will you point to resources where one can use this framework to solve vector problems, particularly also in elasticity? Or
well, elasticity is right now at the state of the art. We just got something working for 2D elasticity, and I'll talk about that in the next lecture, where when I do differential geometry. So you really need vector bundle valued forms because stress is a one form valued n-1 form, and strain is a one form valued one form. So you really need more information than the vanilla DEC provides, which is real numbers, right? In vanilla DEC, the cochains take values in R, but to do elasticity, you need values in some vector bundle. Yeah. Okay. So we have the hot star, we have that, and we have the discrete hot star. And so now let me define the codifferential, the smooth one, and then see what it looks like in the DEC world. So the codifferential is an operator that takes k+1 forms. So it lowers the degree by 1. And it's defined as -1 to the nk+1 hot star d star. That's the definition. So a priori, it's not clear what this should have to do with adjointness, but we will quickly see that it's actually the adjoint of the D operator in this L2 in a product sense. So that's the definition, and now I can write down at least what div grad curl look like. So grad of a function is df sharp. And if you're using a non-Euclidean metric, you would have to actually do this computation to get the real gradient. You'll get the same things. The curl of f is, let's see, you take f, which is a vector field, you flatten it, you get a 1 form, you do d of that, you have a 2 form, in R3, two forms can be confused with vectors because the dimension is 3 choose 2, which is the same as 3 choose 1. So then you do hot star, that brings you back to a 1 form, but then you need a vector field, so you sharpen it. So you see it's deeply involved. The metric is deeply involved. The divergence is, divergence of a vector field is minus codifferential of x or f flat. Okay, but this metric and exterior derivative separation allows for very nice code where everything is separate. You can take the same code and run it on a surface or 3-manifold, hyperbolic manifold, whatever you wish. Okay, so we have the codifferential. So what does the codifferential look like in DEC? The time disappeared. It's not showing any time. Okay, but I just want to pace myself. So the way you do the discrete codifferential is actually quite simple. It is so the way you do that is you write down. So you have your primal cochain complex, let's say CK minus 1x, CKx, CK plus 1x. And there are your D operators, DK minus 1, DK. And so this continues till you reach N, and this continues on this end until you reach C1. And then via this hot star isomorphism, C0, sorry. Via this hot star isomorphism, you can put a star 0 here, and that brings you to dual N forms on the dual cell complex. So similarly, like here, we will have this isomorphism. So these are invertible matrices because in an acute angled mesh, or in general well-centered mesh, the diagonal entries will all be positive. And because the circumcenter is always inside, we are assuming. And so you'll have a diagonal matrix with positive entries. It'll always be invertible. And then let's say, so you have dn minus k star k here, star x here. And you have these. And these, let's say we can write as d dual n minus k. So it turns out, once you have this is easy. I won't show it, but the dual D is, so it looks like something which would be hard to construct because you have this subdivision and gluing and doing everything after that. But it turns out that it's minus 1 to the k dk minus 1 transpose. Just take the ordinary transpose. And so you get, if you want to write down the codifferential, let's say here, the codifferential of a K form will be, so suppose alpha is a K form, a K cochain, then its discrete codifferential, which will be a K minus 1 cochain, will be, you start here, you go down this way, and then come back up. So it will be alpha, you do star K, then you do this dk minus 1 transpose, and there is some sign, and then you do star k minus 1 inverse. So you're back here. So this path gives you the codifferential, the discrete codifferential. And you couldn't do that directly in finite element exterior calculus, or because typically these will not be easily invertible. You could write it down, but it would be not efficient. Thanks. So we have the codifferential, we have its discrete version, and now I guess let's expand on the DRAM complex that we had. So we had this DRAM complex, and now we are going to have this delta, because I will show that it's actually an adjoint. So there will be these, and delta square will also be 0. So it also has the complex property. And the delta square is 0 because if this is delta, when you take two deltas, delta delta will have two stars, they will cancel and you'll get d square, and so it will be 0. So why is this? So this is exactly the sort of generalization of to arbitrary manifolds of the, if you see the vector calculus Dirac complex where you have grad, curl, div, and then backwards adjoints are minus div, curl, and minus grad. This is exactly that. So but why is, so I claim that delta is the L2 adjoint of up to boundary conditions of D. So so what I mean is that it's actually precisely this. If I have alpha and beta in the right spaces, so like let's say beta is a K form, then this will be a K minus 1 form, or if you want to take this to be a K form, this is a K plus 1 form. So this is equal to alpha co-differential beta. So this is why we define the L2 inner product. Plus there will be a boundary term, which I think will be this. So let's see, if let's say we are doing beta is a K form, beta is a K plus 1 form, and alpha is a K minus K form. So alpha is a K form. So alpha is a K form, beta is a K plus 1 form. So the hot star will be N minus K plus 1. So this will be N minus K plus K minus 1, N minus 1. And the boundary of the manifold is N minus 1 dimensional. So it makes sense. So the way you prove it, I won't prove it, but the idea is, again, Leibniz rule. Product rule is so useful. Just the way you do integration by parts by using product rule in calculus, the same idea happens here. So what you want to do is you write down D of alpha wedge. Actually, the other ingredient you will need is the generalized Stokes theorem. So in exterior calculus, there's a unified generalized Stokes theorem. So you don't have to remember different versions. So much so that I have already now long forgotten statements of the Green, Stokes, and divergence theorems. Well, maybe not really, but so you can write all those classical vector calculus theorems as if you have D of omega on a manifold, that's equal to. So, I mean, technically, it's not right to write this. There's a technicality because omega is a form on the M, not on the boundary. So you have to actually pull it back via inclusion, but that makes things ugly. So people just write. So it's very pretty. You can prove many things. And this captures all of the theorems that we know from the Gauss's divergence theorem, Green's theorem, Stokes theorem. These are all combined in one. So with this ingredient and product rule, one can prove. So what you do is you take D of alpha wedge star beta. So the product rule says this is D alpha wedge star beta plus minus. So there's some sign alpha wedge D star beta. So then we will be integrating everything on M. This integral is this guy. This guy will become this because of the Stokes theorem. And here what we'll do is you insert two hot stars with some sign because that's one. And then one star will be star D star, that will be co-differential. And the other star will be needed for making the inner product. So you'll get exactly this guy. So that's how one would prove. So we have not just adjointness, but we have this integration by parts where we know exactly what the boundary condition, the boundary term should look like. All done without coordinates, notice. And in the next lecture, I'll do differential geometry without coordinates, no Christoffel symbols, none at all of any kind, because those are things which are dependent on coordinate. They're not intrinsic geometric objects. So it has been drilled into our head through graduate school that the things that you should worry about are things that you can define intrinsically, geometrically, because then they are clearly coordinate independent. And that seems like a reasonable thing to do in physics. Okay, So once we have this duality, I guess we are ready to go. So these are adjoints. So in R3, this would be grad and minus div, curl, and div and minus grad. If M was R3 and we were doing vector calculus. And so now we'll write Laplacians. So for any, so there are many Laplacians. They all have the same form. So the Laplacian on K forms is d delta plus delta d. So when you are at this end, you say that the codifferential of zero forms is 0. So you just get, so on this, if you start here, you do this excursion, go this way and back. So this would be grad and then this. So this is divergence of gradient, the ordinary Laplacian. That has only one term because you assume that this end is 0. And this also has only one term on the right because the d of any n form is 0. You can only accommodate n forms on an n-dimensional manifold. But in between, for example, if you were doing vector calculus, these were vector fields. This would be curl, this would be grad and div. So this would be grad of curl minus gradient of divergence. So that would be one vector Laplacian. Then another vector Laplacian would be sitting at where the two forms are, and so on. But in general, this is called the Hodge-Laplace operator. And it generalizes to any dimension on any manifold, the Laplacians that we know. So this Laplacian has wonderful properties. One of the properties is that one can, just like the Helmholtz Hodge decomposition, one can do, so let's assume for now that the boundary of the manifold is empty to simplify things. Like, for example, you have a torus. Then the Hodge decomposition says that the space of K forms can be decomposed into these L2 orthogonal spaces, which are the image of D plus, I won't write this because I'm sure I'll get confused, image of delta plus, so this is direct sum and this is orthogonal direct sum. So, right, plus these things which I will write as HK, where HK is the kernel of this Laplacian. And there's a theorem called the Hodge isomorphism theorem that says that this kernel of the Laplacian is isomorphic to the cohomology space, which I had mentioned earlier. So this is the kernel mod image. So things which are gradients, but things which are curls, but not gradient of anything, that sort of thing. So I don't have time to go into cohomology theory, but I will at least draw a picture. So this kernel is very important. And when you're trying to solve Poisson's equation, so when you solve Poisson's equation, the kernel of the Laplacian is, the dimension is the number of connected components. That's why you fix, let's say at a vertex, you fix the value because otherwise the thing will not be well posed. But so where should I go from here? So let's see. So this is fine. This Hodge decomposition in this kind of a manifold situation is a little bit harder to prove. But this infinite dimension, this is just linear algebra using Gilbert-Strang's 4 fundamental subspaces, the null space, the column space, and their orthogonal complements. So I think I have time to quickly sketch that idea because Hodge decomposition is very important idea. So let's say you have inner product finite dimensional vector spaces U, V, and W. So there's an inner product defined on all of these. You can take a dot product of 2 vectors. And you have operators A and B such that A followed by B is 0. And take the adjoint operators, which I'll just write as with T. So just think of them as matrices. The transpose of that is A transpose, B transpose. So that's also 0. This is like your exterior derivative and this like your codifferential. So you will see that V decomposes uniquely into image of A. It decomposes orthogonally into image of A plus image of B transpose plus the kernel of Laplacian, where Laplacian is using this pattern, going this way and that way. So see, you just go like this and you go like that. That's what d delta plus delta d is. So Laplacian is, you start here and you can do this followed by that, and this followed by that. So let me see if I can do this from memory. So I think the way this will work is you have V can clearly be written as image of A plus the orthogonal complement of, so some space plus its orthogonal complement. So the image of A, the orthogonal complement of the image is the kernel of A transpose. So we have that V is image of A plus kernel of A transpose. But we have BA is 0, but we also have A transpose, B transpose is 0. So the kernel of A transpose contains the image of B transpose. So what we will do then is write this as image of A plus image of B transpose, which is sitting inside the kernel of A transpose, plus the rest of So what is the rest? The rest is orthogonal complement of the image. So the rest means the orthogonal complement of this sitting inside the kernel of A transpose. So this is just the orthogonal complement of the image. I'm used to saying kernel and image. If you are used to, you can just think kernel is null space, image is column space. So we have kernel of B intersect kernel of A transpose. So therefore I can decompose V into this orthogonal decomposition. So if I have not made any mistake, then this should be equal to the kernel of the Laplacian. So one direction is clear. So if something is in the kernel of B and kernel of A transpose, if I feed something which is in the kernel of B and the kernel of that, then it's clearly in the kernel of that. To see the reverse, let's take something in the kernel of U, the kernel of Laplacian, and take its inner product with U. So this is so Laplacian is A transpose U plus, okay, A transpose plus B transpose B applied to U. So that's what we are doing. So this is A transpose U dot A transpose U plus BU dot U. So it's a sum of two squares. And so if something is in the kernel of this will be 0. So therefore this will be 0. So each of these terms will be 0. So indeed, not only is this a subset of the kernel of the Laplacian, but this is actually equal to the kernel of the Laplacian. So this is just a linear algebraic view of Hodge decomposition. Any question? And this is a sort of variant of what is called Helmholtz Hodge decomposition people use in fluid mechanics and many other places. Okay, so we have enough time, I believe, that we can do just a sort of pictorial view of what these harmonic forms look like. Any questions? Suraj, question? Oh, okay.
One quick question. So are there generalizations of the Hodge Laplace decomposition for essentially higher forms in the sense.
Yeah, for higher forms.
You
So like for vector fields, we call it, like engineers call it Helmholtz decomposition, right?
Right.
This is for any K form.
Okay.
I was just
And
doing,
that has to do with, let's say, d squared delta, and then delta d square.
Yeah. Adjointness, all of that stuff.
Okay.
Yeah.
I have a small technical question. You say the kernel of Laplacian is HK?
Yes.
I mean, on the bottom on some column, it's HK, and then at the top of the next column there is an approximate.
Not
sign.
approximate, sorry. This is isomorphic too. So this is a
Isomorphic.
theorem, right? So this is Hodge theorem or Hodge-Dirac isomorphism theorem, that this topological thing is, this is a finite dimensional vector space for a manifold. It's a topological thing which captures the topology of the manifold. It turns out to be isomorphic as a vector space to the kernel of this analytical operator, this Laplacian. So that's a very nice connection between analysis and topology.
One quick question I want to ask. So wherever there is, this wedge product with the Hodge star,
yeah,
somehow there is the metric is built into it.
Yes, because we defined the Hodge star by first defining the volume form, which was induced from the metric, then defining the inner product of forms which use sharp, which also use metric.
Right, so all of
deeply
this
embedded.
actually...
Yeah, it's deeply embedded, but sort of condensed into one operator, and with resulting very clean development of everything.
Though you would imagine, I mean, intuitively that the metric has, there's a length scale built into it.
Yeah.
Here, is that still true? Because...
So that confuses me, because that's how physicists think. And so maybe we can talk about that later, but yeah.
The association of the algebraic, the kernel, and that's the cohomology.
Yeah, so that's an algebraic thing, yes. But it's Dirac cohomology, which is isomorphic to, if you triangulated the manifold and computed simplicial cohomology, one can prove that the two are isomorphic. Yes. So there's something very combinatorial, which is the same as something that comes from calculus, is the same as something that comes. Yeah.
Is there presumably there's a connection then with Atiyah Singer? Or is this
no, Atiyah Singer has to do with torsion.
Okay. I thought it was also a similar sort of index of the kernel of some differential operator.
Yeah. Yeah, but I don't know much about the Atiyah Singer index theorem, so what I say will probably be wrong, but this is different. Yeah, I don't know what the corresponding sort of isomorphism theorem there is, but I don't want to say something incorrect. Okay, so now that we should have some sort of picture of what these harmonic forms look like. So they are very pretty, and a harmonic one form on a torus, if you view it as a proxy, there will be the kernel of the Laplacian. So kernel of the Laplacian on one forms on the torus will have dimension 2. And so the kernel will be 2-dimensional, and so those are harmonic forms, and those harmonic forms look like, if you were to visualize them as vector fields, they would look like vector fields that go around this way and vector fields that go around this way. If you can do these things with boundary also, it's a little bit more like, so you have to use relative cohomology in some place or something else. But the harmonic form looks like this for the one Laplacian. So that's why when I showed on the first day the picture of the annulus computation, the Lagrange nodal finite elements were not able to capture the harmonic form properly. And the Raviat-Thoma, which is like the Whitney form, is able to. So this is an annulus, this is a torus. So the kernel captures the topological features. And if you want to solve Poisson's equation, you had better be careful that you remove the kernel first. So this is the Hodge-Laplace problem. there is also the Helmholtz problem that you can do. Like the curl problem would be assuming codifferential is 0, it's delta du is equal to lambda u, for example. That would be the curl problem. But that's Helmholtz problem. This is Hodge-Laplace problem. So for K forms, so we're given F, which is a K form, find a U, also a K form. And of course, when we do these things, we do properly with the right Sobolev spaces. So you use things that are equivalent to H, which are like H1, H curl, H div, L2. So there's a generalization of that. It's called H lambda K. So there are Sobolev spaces that one works with. But I don't want to get into analysis. So let's just think about that. So the first thing you have to do, you will not be able to find something unless you remove the harmonics from it, because this will always, no matter what you give it, it will kill the harmonics, right? Harmonics are in the kernel. So you can't really solve this problem until you have subtracted the projection to the harmonics. So let's say we have done that. So we have assumed that we have subtracted, let's call this P, and we are solving this problem. But then why not just call that F? So we have F, which has now no harmonics, and this is the problem that we'd like to solve. So if you were doing DEC, you can do it in mixed form or direct form, because you can do it in finite elements also, but it will be inefficient because of the inverses involved. But let's write the Hodge zero Laplacian. And you have to do this in such a way that U is orthogonal to the harmonics. So you have to find, to make it well posed, you have to find a U which is orthogonal to the harmonics. So whenever you solve these problems, the first thing you need is a basis for the kernel of the Laplacian. And for ordinary Laplacian, that's the kernel is one-dimensional, and you get it by, so you get solutions up to constants. So you just fix at a vertex some number and solve the rest. So if you were to do this, you could just write, I hope I have the, right. It's too far, so I'll just draw it here. So let me just do it for C0x. We are doing in 3D, let's say. C1x, C2x, C3x. And there are the Hodge stars taking you to the dual cell complex. This is dual 3 forms. Dual 2 forms. Dual 1 forms. And dual 0 forms. So this is D0, and so this Laplacian will be D delta. So you can do D0U, and then, so it's, sorry, delta D, right? So the delta will be star 1. Then this will be transpose of that, so up to sign. And then you do star 0 inverse. And that you say is equal to F. And so then you can just take this to the other side if you wish. And solve this problem. This is a square matrix. And make sure that you're doing it orthogonal to the kernel. So making sure that you set, so these are things that live on vertices. You fix the value at a vertex so that you solve up to constants. By doing that, then you'll get a unique solution. So you have a linear system, a square linear system. And so where do you get F? So F is given to you, you just sample it at the vertices. And finite element people will get upset about that. They'll say, oh, you have to do, what if it's in L2? So let's just take everything smooth. So you sample this, these are the Hodge stars we had, and you solve this problem. And this is actually exactly the stiffness matrix of finite elements. And this is the mass matrix that you would use in finite. This is exactly that same problem. If you were doing finite elements, the mass matrices would be different, but it would be the same same problem, at least the form of it. So let's do one more. So I'm not, so everywhere here, U should be perpendicular to the harmonics. And so here we can do this excursion. So this is D1 star 1, D0 transpose star 0 inverse. So that's doing D delta. And then we want to do delta D. Oh, I think I might have mixed up things. So you go this way, you end up at 2, right? D1 U, you end up here. So then you have star 2, and then D1 transpose, and star 1 inverse. Plus, so this is delta D, and you have to do D delta. So you're starting here, the delta is star 1, D0 transpose, star 0 inverse. And this is equal to so here F is a one form, U is a one form, and you have all the matrices. You just write down the system and solve it. And so you wouldn't, I might have messed up some. Yeah, right. So yeah, they're right. So this is delta, and then we need, this is delta, and then we need a D0, right? So you could get rid of, so you might say, oh, I'm doing finite elements. My matrices are sparse, but not diagonal. So I can get rid of this inverse by moving it here, but you would still be stuck with that, and you have to do some linear algebraic tricks to get rid of that. So this is one reason, a naive reason why finite element people would not do, they will do the direct problem because you can get rid of the inverse this way, exactly this way. But they wouldn't do this directly because this inverse would be very expensive. And if you were doing two forms, K forms in general. But let's do the mixed formulation. So in DEC, this is no problem because these are just diagonal matrices.
So one quick question. So
Yeah.
when you said you want to look for the harmonics removed part, how
Yeah.
do you ensure that when you're doing this?
So you set up the linear system in such a way that the constraint is, you have a basis for the harmonics computed.
Yeah.
And then you make sure that you're orthogonal to that.
Practically, when you do it, so you pick a basis which is orthogonal to the harmonics of your underlying.
No, you pick a basis of the harmonic form by using topology. You compute the, you compute on the dual homology things, and the dual of that will be the cohomology things. So you can compute harmonic forms in various ways.
But in the discrete case, how do you?
Yeah, you just do the computation. And,
Okay.
yeah. In fact, there's a very nice thing that one can do, which is that, so things which are in the same cohomology class, so they differ by D of something. So things that are in the same cohomology class, in every cohomology class, this L2 minimizer is a harmonic form. So you can use algebraic topology to get a basis for cohomology, and then do a least squares problem, and you'll get a beautiful harmonic form. So, yes.
I had a question. So on the equation here, so why can't we have an harmonic part in F?
Why do we have a?
Why can't we have an harmonic part in F?
If you had a harmonic part in F, that will be killed by the Laplacian, so you'll never be able to find a U. Okay, so let's do mixed formulation. I think I have time. Yeah. So how would you do this if you were like when we did, I showed you D'Arcy flow where velocity, sorry, you have pressure. The original problem is Laplacian of pressure is F, and then you have, you set up velocity is negative gradient of pressure and divergence of velocity is the right-hand side. So let's do that in general case. So we want to solve d delta U plus delta du equals F. And what we will do is, because we don't want to do codifferentials because it involves, and we are doing weak forms anyway, we can get rid of codifferentials by adjointness. But this one would be hard, so we'll want this to be, let's define this to be the new variable. So for example, if this was pressure in D'Arcy flow, this would be a 2 form and velocity would be the codifferential of that, the 1 form. Those will be the fluxes. So we want this. And then if we have this, we should be able to write this as d sigma plus delta du. And we will solve for u and sigma. So we'd like to solve these two equations. We can get rid of this and that via adjointness. So that's the plan. So let's do that here. So you do, so let's say minus sigma plus delta u equals 0. That's what we would like. And then d sigma plus delta du equals f. So you take test forms. So sigma is a k minus 1 form, u is a k form. So you will take test forms tau, which will be k minus 1 forms, and v's, which will be k forms, and you do a weak formulation. So you do minus sigma dot tau plus delta u dot tau equals 0 for all tau, and d sigma dot v. These are the L2 inner products that we had earlier worked out for forms, plus delta du dot v equals fv. Let's assume that there are no harmonics. So let's assume, otherwise you will have there are no harmonics in f, and then there'll be a separate equation that u should be perpendicular to the harmonics, which I won't write down. So let's just look at these guys. So if you do the integration by parts that we had done earlier, you will see what the boundary condition should be. And so this, if you do integration by parts, you have, so we'll write down the actual matrix in a minute. But, and this is agnostic to which inner product you're using. It could be finite element inner product or DEC inner product, doesn't matter. So this plus u dot d tau, and then there will be a boundary term. I think it will be something like that. And then d sigma dot v plus du dv plus, I don't know, plus or minus, I can't remember. And I think this will be v dot star du. Is that right, Kaushik? Something like that. So this is 0, and this is f dot v. So you can impose, for example, homogeneous boundary conditions in a natural way by just throwing out this integral. And you'll see in finite element exterior calculus papers that star u and star du are one type of conditions. The other is you can set sigma. If you do homogeneous, you can do sigma and u 0 on the boundary by building it into your finite element space, and you pick your trial functions from the same space. So then you can set u equal to 0 or sigma equal to 0. These are the two sets of boundary conditions that you will see. And one corresponds to Neumann, one corresponds to Dirichlet, and all of that. And so in electromagnetism, there will be other names, magnetic boundary conditions, curl of this cross that, whatever. It's all captured in one. Okay, so how do we discretize this? Well, just the way you do in finite elements, you write bases and blah, blah, blah. And so let me write this as tau, which is a k minus 1 form. So I will write this discretely. Tau transpose star k minus 1, there's a minus sign, sigma, plus tau transpose d k minus 1 transpose star k u. And let's throw away the boundary condition for now. And this is v transpose star k d k minus 1 sigma plus v transpose d k transpose star k plus 1 d k u equals, throwing away the boundary condition, V transpose star AF. And since we have, so this is supposed to be, we are doing the weak form, we want this to be true for all tau and all V. So in the linear system, we can drop this. And so the matrix that you get looks like this. You have minus star K minus 1, dk minus 1 transpose star K. Here are your sigma variables which live on K minus 1 simplices, U variables which live on K simplices, 0 star KF. And then the next equation is star K dk minus 1 and dk transpose star K plus 1. And so notice that this is a saddle type matrix, which is symmetric because star is symmetric, it's a diagonal. And this is the transpose of that because star is a diagonal matrix. So that's the linear system one solves. So it's not just abstract nonsense, but actually you can write down very concretely. And the only, so if you were wanting to do mixed form in DEC, you would use diagonal mass matrices here. If you were using finite element exterior calculus, you would use the lowest degree finite element mass matrices. So what are those? Where do they come from? So I think that's an important topic to cover. So we'll talk about just the lowest degree because that's what matches DEC. So the shape functions are what are called Whitney forms. So Whitney forms, they were invented by Hassler Whitney, and who was a geometer, and they look like this. So let's say you have a K simplex sitting inside some higher dimensional simplex, like you have a edge inside a tetrahedra. Or you can have vertex inside a triangle, vertex inside a tetrahedra, whatever. So you have some lower dimensional thing, simplex, which is a face of a bigger simplex. So then you can define these Whitney forms for this. Let me write this in this cumbersome way. So this is the Whitney form corresponding to this face in that simplex. Both are important. And they will be written simply in terms of barycentric coordinates. So this will be, so suppose this is a K simplex. So in fact, let's take it to be this. These are the vertices of that simplex. So then you would do K factorial summation minus 1 to the I going from 0 to K, lambda I, d lambda 0 wedge, d lambda I missing, d lambda K. So this hat just means this term is missing. So it will be a K form because it will be a wedge of K1 forms multiplied by this. So I want to give you some intuition about this. It's a very beautiful shape function that Whitney invented, very geometric. It has beautiful properties. Like for example, so if I call map W something that takes L2 K forms on a simplicial complex so it takes cochains. It's a shape function. It takes the degree of freedom values and produces a piecewise smooth form. And so this is what I want to sort of sketch out for you. And this works for every dimension. It has wonderful properties, which is why finite element people love it. And the main thing is that one nice thing is that D commutes with the co-boundary. So which means that I can take a cochain, do its co-boundary, do a discrete D, and then do the shape function interpolation. I'll get the same answer as if I interpolated those degrees of freedom and did the smooth D. You'll get the same smooth form inside. And it's smooth all the way up to the boundary of the simplex. So that's one property. The other is that when you pull back the Whitney form from two sides on a n-1 dimensional face, they match, which corresponds to, if you would be thinking of them as vector fields, that they have tangential continuity. So that allows you to do various spaces, H-curl, H-div, by rotating. So that's the idea. So I want to just sketch that for you. So let's do this. Let's first do this on a single triangle. So this is my triangle. Let me, don't have to orient it. And so the Whitney form corresponding to the edge 0, 1 sitting inside the triangle 0, 1, 2. So this will be, it's a one form, so 1 factorial. And the terms are lambda 0 d lambda 1 minus lambda 1 d lambda 0. So I'll just not write this. So if I sharpen it and I have standard Euclidean metric, then this looks like that, which is easier to visualize as a vector field. So this is assuming, no, I guess not assuming, it's a gradient in whatever metric, but let's assume Euclidean. Let's assume Euclidean. So what does this look like? So we are on this edge. Oh, these are barycentric functions. So these are lambda 0 is the one that's 1 at vertex 1 and it's affine, and 0 on all the other vertices. So for example, this lambda 0 is something which is 1 here and 0 on this edge, and it's linear. So so let's look at this edge. When I'm here, lambda 0 is 0, right? Lambda 0 is 0 on this whole edge. So the barycentric function of that guy is 0 at this point. So this term goes away. And we just have to deal with minus lambda 1 grad lambda 0. So grad lambda 0 is that function. So grad lambda 0 is perpendicular to this line. And so lambda 1 will be 1 here. It'll point because of the minus sign in this direction. And so this will continue to be 0 on this edge because it's the barycentric function for this guy, which goes to 0 on that edge. So as you go down this way, the lambda 1 will go to 0. So what you will have is these linearly reducing vectors on this edge. On that edge, lambda 1 is 0, so we can throw away this guy because lambda 1 is 0 completely on this edge. It's 1 here and 0 here. And so we just have to contend with this guy. And let's see, if I am here, lambda 0 is 1. And gradient of lambda 1 points towards, it's this affine plane, it points in that direction. So it's perpendicular to this edge. And as I go down this edge, lambda 0 falls to 0 on this edge. So this goes down to 0. So if you do this, what you will get is a vector field that looks like it's perpendicular here and rotating in this way. So when you do the line integral on this, it will be 0. But if you do the line integral on this, you'll get 1. So that's a property it has. And if you have a different guy here, it will have the same property. And so you will have tangential continuity. And this works in any dimension. So how much time? Okay. So with these shape functions, one can compute the mass matrices for finite element exterior calculus. And then these star Ks that you are seeing there, they will be the finite element mass matrices. So the exact same equations will work. So the reason they are not, the reason the mass matrix is not diagonal is because, for example, if you look at this triangle, this guy and the Whitney form of that guy will interact. So when you take the inner product, you will get a term due to that. So you assume outside everything is 0. So, but for both these triangles, so whatever is the support of the edge is where the mass matrix entries will be. It will interact with, so it will have 1, 2, 3, 4 entries in that row corresponding to that central edge. 5 actually, itself and 4 others, whereas the deck would have just 1 itself. So it is still sparse because it has local support, but it's not diagonal. So inverting it is hard. So I think I've covered that part. And I think in the last, Yes.
One quick question. So in the example that you showed in the first class,
Yeah.
Where you had, let's say, something like with a non-trivial topology,
Yeah.
it's important to capture the, it's important to use the Whitney forms,
Yeah.
and that captures the, the vertical structure accurately. So what was missing in the other case? And
There's something missing from that function space.
Okay.
Yeah, if you use Lagrange. So, other things are like, so there's exactness, like on a single simplex, you want, since the topology of the single simplex is trivial, you should have kernel is equal to the image. Image is always subset of the kernel, but you should have equal. And if you work out a calculation, Kaushik just showed me a few days ago, if you take Lagrange elements, take the gradient, and take Lagrange with 2 entries for the vectors, the space is too big, the kernel is too big. But if you do Whitney forms, it's exactly equal. So exactness is preserving the homology, cohomology is very important, cohomology. That's why Kaibo's paper is many facets of cohomology. Very beautiful survey paper that just came out recently. So, okay, so the last thing I want to do is, can you only do Poisson's problems and Helmholtz problems, or can you do anything more? So, for example, we do have a paper in JCP on 2-phase flow and Navier-Stokes on surfaces without assuming any smoothness, just piecewise linear mesh. You can do Navier-Stokes. So how do we do this? There's nonlinearity there. So there is u dot nabla u. So that kind of nonlinearity or a product nonlinearity you can handle in the following way. So first of all, let me just introduce contraction. So contraction is this operator given a K form. So, so let's say you have a vector field and you have a K form. Then contraction produces a K minus 1 form. And all you do is you stick X into the first slot. And so you have 1 slot less, it's K minus 1 form. And Lie derivative, I won't be able to sort of give you anything more intuition than just the definition. The Lie derivative is d by dt at t equal to 0 of the pullback under the flow of the vector field for time t of the form. And so if phi t is the flow of that vector field or flow for time x. So it tells you how, so you have a manifold, let's say, and this, you have a vector field. Phi is a map that tells you where each point goes if you solve the ODE for time t. So it's called the flow map. So it's a diffeomorphism of the manifold to itself, assuming some properties of the differential equation. So that's fine. It's sometimes called Fisherman's derivative. It's kind of measuring the rate of change of this tensor, antisymmetric tensor. You can do it for any tensor, but let's just do it for forms. And there's a wonderful formula called the Cartan formula. Some people call it magic formula, Cartan's magic formula, which says that the Lie derivative is this formula. So which has very nice connections to various things. So it turns out that this u dot nabla u term is the Lie derivative of u flat along u minus 1/2 of d of I think u flat, yeah. So which I can write like that. So if you know how to do contraction, the thought was then you could do Lie derivative, so you could do that. So now we knew how to do D, we knew how to do wedge, we knew how to do star. So I rediscovered a formula in my grad school days that contraction, it's now showing up in double forms in various adjointness things. It's equal to -1 to the k n minus k star of alpha wedge x flat. So this has a whole lot of metric built into this. There's a flat here, there's a star, another star. This has no metric. This is just inserting x into the first slot. But it turns out that metric cancels out in a very nice way. But because we knew how to do each of these things, at least for proxy vector fields, like things which are actually one forms. So, okay. So let's just check at least the degree count. So this is supposed to be a k minus 1 form. Let's check this. This is a 1 form. Alpha was a k form. So this is n minus k form. So this thing is n minus k plus 1 form. And then when you take the hot star of that, that's n minus k plus 1. So n k minus 1, that matches. So at least it has the right degree. So that sort of type checking is important. One way to, so the idea of doing this u dot nabla u is to do it via the Cartan formula. And if you have divergence free, then one of the terms is gone, and then you just need to implement contraction, and it's D using wedge and Hodge, and that's what we had done. So by the way, one thing I've been doing is, so in finite elements, you can only do things where the degrees of freedom are, I mean, I don't know only, but typically the degrees of freedom are on the primal simplices. Right? They're associated, like in edge elements, in Nedelec edge elements, they're associated with the edges of the tetrahedra, face elements with the face so on. So in DEC, you can solve the PDE using your degrees of freedom on the dual mesh. So you can do the whole problem on the dual side. You can do the whole problem on the primal side. But in both cases, both are involved. You don't need to store the dual, by the way, because with every primal, there is a corresponding dual. So in terms of bookkeeping, you can track the duals. All you need is the hot stars. All you need is to measure the volumes and areas and so on, and store those in diagonal matrices, and then you can throw away. You don't actually construct this subdivision and the dual cell complex or anything. It's just you collect this measure information, and you just leave it for. The bookkeeping is just that for every primal there was a dual. So, but anyway, the point is that you can do the PDEs on the dual, and some people have, like in our Navier-Stokes, our main variable U was living on the duals, and the pressure was constants on the triangles. That can be done. Okay, so I want to show you one thing, which is that this contraction, I've realized recently, but I guess many people know this, is actually L2 dual of the wedge. So alpha is a K form. This is a K minus 1 form. So beta must be a K minus 1 form. And K minus 1 plus 1 is K form. So we are doing everything okay here. So, and I guess the proof is just use this formula, insert it, and play various tricks with removing and adding hot stars. And it's very simple to prove that. So some people write contraction as hook, like that. And then it's nicer to see the duality. So I think I can stop. I'll stop here. And I don't have anything more to say about this at this point. Yes.
Let's thank Anil.